Okay, so let's start. Welcome to the third session of coastal ocean and inland waters. So this is the third part, and we have 5 speakers. Each speaker has 15 minutes in total. So at the 10-minute, I will give you a warning reminder. You have 2 more minutes to speak, and we will leave 3 minutes for questions and comments. So without further ado, I would like to introduce our first speaker, Kent Moore, talking about evolving relationship of Nares Strait ice arches on sea ice along the strait and the North Water. Kent?
Okay, just start sharing here. Okay, hopefully you can see my slides here.
Yes, I can hear you well, and the slides.
Good. Okay, so I want to talk about the relationship between ice arches that form along Nares Strait and the North Water. I want to, first of all, just acknowledge my collaborators, Steve Howell and Mike Brady from Environment and Climate Change Canada. So this is a satellite image from a couple of years ago showing essentially the southern end of Nares Strait, Ellesmere Island, Greenland here, and there's sea ice in Kane Basin. And there's this presence of this arch-like feature here, which is an ice arch, which formed, this image is taken from early March. It formed probably in January or so and remained stable until June. And downstream of the arch, you can see this area of open water, which is the North Water. So just to give you a bit of a perspective where we are, so essentially Nares Strait is this waterway between Ellesmere Island and Greenland. It connects the Lincoln Sea to Baffin Bay and then out into the subpolar North Atlantic. These are 2 SAR images taken in December 2020. In the first image, which is on December 1st, 2020, one can see essentially sea ice moving down through Kane Basin and into the region of the North Water. 2 weeks later, an arch had actually formed here, and one can see now essentially that there's now open water south of the arch, and less ice concentration south of the arch, and this essentially is the arch, and then the formation of the North Water this year. And so when these arches form, the transport down through Nares Strait can cease for upwards of 6 months or so at a time. The red line here is a flux gate, which we've put in here. And by using the SAR imagery, one can essentially calculate the ice motion across this flux gate. And this is what you see here. So this is the ice area flux across that gate. Positive ice area fluxes mean the ice is moving southwards. And so you can see in November here, the ice is moving southwards. And then when the arch forms, somewhere around the 1st of December 2020, essentially the transport went to 0 and remained 0 through June. Okay, so this is the impact the arch has on the ice area flux. So again, as I mentioned, south of Smith Sound, one has this large area of open water known as the North Water, or the Pikorsarorsuaq in West Greenlandic. And this is the Arctic's largest and most productive polynya. And a number of years ago, there was a nice report written essentially on the future of the North Water from the perspective of the Inuit communities who live either on Ellesmere Island or in Greenland. And one of the concerns is that the Arctic continues to warm. We've observed that these arches are becoming less stable, they form less frequently, they collapse earlier. And so there's a concern that this weakening will impact both the ice transport down through Nares Strait. It will increase the ice transport down the Nares Strait, and it will also potentially impact the North Water. And this is an article several years ago talking about essentially the impact that this plug or the ice arch has on keeping the oldest ice present, which is the ice up here in the Lincoln Sea, as well as potentially impacting the North Water. So in this talk, what I want to do is I want to compare and contrast winters from this period of time here with or without the presence of a southern arch. And hopefully it'll help answer the question, what will the now look like if Nares Strait ice arches no longer form? Sorry. So to do this, what I'll use an ice arch climatology, which is based on the work of a number of people, including Ron Vincent and Krylov et al., and work that my team has done. And essentially, this essentially gives you these winters from 2003 to 2022, and essentially categorized by whether a southern arch formed, no arch formed, or a northern arch formed. And so with that, I'm also going to use sea ice concentration data from the AMSR E/2 instruments, which were retrieved using the ARTIST retrieval from the University of Bremen. I'll also use 10-meter winds from the Copernicus Arctic Regional Reanalysis. This is a new regional reanalysis of the Greenland area at very high spatial resolution, 2.5 kilometers. And I'll also use ocean color retrievals from NASA's Ocean Biology Processing Group. I'm going to focus on May because May is the last month that usually has an arch present. The results aren't much different if one looks earlier in the winter as well. So here shows you essentially, what I've done is I've categorized the sea ice concentration during May into 3 categories: when a southern arch is present, when a northern arch is present, and when no arch is present. So in this period of time here, there are 14 winters that had a southern arch. There are 3 winters that had a northern arch, and there are 3 winters which had no arch present. And so first of all, looking at the southern arch case, you can see that when you have a southern arch present, one has 100% ice cover through essentially Kennedy Channel and into Kane Basin. And then south of the arch, which usually forms somewhere in the vicinity of Smith Sound, one has open water, or at least reduced ice cover, 25%, 50%, and 75% down here. If you look at the case where there's a northern arch present, one can see the representation of the arch here. So again, now one has a very different picture down through Kennedy Channel and Kane Basin, with open water present through much of Kennedy Channel and down into Kane Basin. And then again, south of Smith Sound, one has open water, or at least reduced ice cover present. When there are no arches present along the strait, again, one has a situation somewhere between these two, with regions of reduced ice cover in Kennedy Channel and the northern parts of Kane Basin, and again, reduced ice cover south of Smith Sound. So what I'm going to do going forward is I'm going to collapse these 3 categories into 2 categories, either the presence of a southern arch or no southern arch. And so the no southern arch case will combine these 2 cases together. And so these are the composites that you get here. This is the same as I showed before, the southern arch composite. This is the no southern arch composite. And again, you can see indications of regions of reduced ice cover through Kennedy Channel and into Kane Basin. And then again, reduced ice cover south of Smith Sound. And again, if you just compare the ice cover in the region where the North Water is, again, they are similar. There are some differences. There's a bit more ice concentration on the western side of the channel, but essentially one has open water, at least reduced ice cover present in both of these cases here. So to get things a bit more quantitative, what I'm going to do is I'm going to average along the center line of the channel. So this is the center line here, and I'm going to look at parameters as a function of their distance along this center line here. The first one I'm going to show you is this is the meridional wind component, and this is the composite for the southern arch case. This is the no southern arch case, and this is then the average along the center line, going from 82.5 degrees north, which is up here, down to 76 north, which is actually somewhere around in here. First of all, you look at the composites, you can see that there's 2 regions where there's high wind speed along Nares Strait. One of them is in the vicinity of Kennedy Channel, and the other one is south of Smith Sound. And you can see if you compare the southern arch to the no southern arch case, again, wind speeds south of Smith Sound are very, very similar. And if you look along Kennedy Channel and the northern part of Kane Basin, one can see wind speeds are much higher. They're 2 meters per second higher in this case than in this case here. And again, you can see that when you look along the center line, again, this is the region of Kennedy Channel here, and you can see that the wind speeds are higher in the case where there's a southern arch present, sorry, when there's no arch present compared to a southern arch present. Whereas you look over Smith Sound, which is in this region here, the wind speeds are very, very similar. So the 10-meter wind speeds are higher along Kennedy Channel and Smith Sound. In both of these regions, there's a narrowing of the strait, and that leads to higher wind speeds. In the absence of a southern arch, the wind speeds are higher over Kennedy Channel. And in fact, the difference between these two composites is statistically significant at the 0.01 level. And then in the vicinity of Smith Sound, I'm now going to jump forward. Yeah, I'm just about finished here. So I'm just going to jump forward to looking at ocean color. So this is chlorophyll A, and you can see again, in the no southern arch case, there's in fact chlorophyll present, productivity present right through the strait, but in the vicinity of the North Water, they look actually quite similar. So there's non-zero ocean color all along the strait in the absence of the southern arch. Over the now, in fact, they're quite similar. So just to conclude then, what I've done in this talk is I've compared and contrasted winters with or without the presence of the southern arch along Nares Strait. The ice concentration along Kennedy Channel is lower in the absence of the southern arch, and that's most likely due to higher wind speeds that help sweep the ice southwards. Ice concentrations over the now were similar in both cases, and the same was true for ocean color. And so this then suggests that the now will remain present with similar levels of productivity, of course, all other parameters being unchanged as the region continues to warm and arches weaken. So thank you very much.
Thank you very much, Kent, for a very nice talk. And now we can have questions or comments for Kent. And yeah, please put your questions or comments into the question answer tag. Okay. I have a question. So yeah, so we have now this called surface water and ocean topography satellite launched and the data being available. So do you think those data, can be used to help you to detecting these things and to study this sea ice arches?
I certainly hope so.
Yeah.
I'm looking forward to that data. Yes, for sure.
Yeah. Okay. So if there's no further questions, and we'll move ahead. Thank you, Kim. And the next speaker is Spenser Ross on the examination of Wrangel Island sea ice thickness at Dipole.
Okay. Can you hear me and see this?
Yes, I can see the screen, your presentation, and hear you well.
Okay, great. So today I'm going to talk about a sea ice thickness feature around Wrangel Island, which I worked on with the help of my supervisor, Kent Moore, and collaborator, Kristen Ladra. So Wrangel Island is located in the western Chukchi Sea to the north of the Bering Strait between Siberia and Alaska, and it has an area of around 7,600 square kilometers. So in this presentation, I'm going to show that climatologically, an ice thickness dipole forms at Wrangel Island with thicker ice on the east and thinner ice on the west side. And the dipole is generally formed due to the advection of ice from the east to the west, and it is blocked by the island and accumulates on that side. A reversal in the flow can cause the dipole to have the opposing sign with thicker ice on the west. I'll provide more detail in the following slides, but first I will provide a background and motivate the investigation. So Wrangel Island is an important physical and biological location. It is home to many species throughout the year, including polar bears, walrus, seals, and other marine mammals. It is especially important, an especially important location for polar bears of the Chukchi Sea subpopulation. These polar bears spend much of their time in the summer on the island as the ice retreats, and during the fall and winter, adult female polar bears den there and give birth on the island. Another important feature of the island is the Wrangel Island polynya. So typically in June, a seasonal polynya opens on the west side of the island and can creep up to the north side of the island. So this is a picture from a NASA satellite image from June of 2023, showing this area of open water here to the west and up into the north of the island, which marks this polynya. This is a latent heat polynya, and it plays a role on the thin side of the dipole, which forms across the island. Increased ice thickness to the east of the island has also been observed during early expeditions as pressure ridges when flowing ice converges with the ice surrounding the island. So one of these expeditions is the Canadian Arctic expedition in 1913, where this ship, the Karluk, ended up becoming trapped in the sea ice off of Alaska and drifted westwards towards Wrangel Island and eventually sank there right near Wrangel Island in 1914. The crew sought refuge on Wrangel Island, so they report and describe running into a series of massive pressure ridges and spending nearly a week cutting through them to reach the island. So here's a picture of some really thick ice with the expeditioners on top trying to get to the island. Okay, so this figure shows the mean sea level pressure from ERA 5 and the 10-meter winds from 1979 to 2022. So over the long-term mean, we have this high pressure, high sea level pressure region in the Beaufort Sea known as the Beaufort Sea High. And the Beaufort Sea High strongly influences surface winds, ice motion, and ocean circulation in the Western Arctic. The climatological winds circulate anticyclonically around this region of high pressure, and this is known as the Beaufort Gyre. The anticyclonic circulation forces easterly winds and ice motion towards Wrangel Island on the long-term mean. However, reversals in the motion, typically due to a collapse in the Beaufort Sea High, would force westerly wind and ice towards Wrangel Island. So here in this figure from data with the International Arctic Buoy Program, in the winter of 2016, we have this climatological circulation around the Beaufort Gyre, and then this forces that easterly motion towards the island. And then in 2017, the Beaufort Sea High collapsed and led to a reversal, especially in this region here. And then we get westerly motion towards the island. So during the climatological easterly ice motion towards the island, ice is blocked by the island and accumulates on that eastern side, increasing the ice thickness and creating those pressure ridges. Ice continues to flow to the west, and we get a region of decreased ice thickness. So the dipole in sea ice thickness is formed like that, and it can be reversed when the Beaufort Sea High collapses and the flow is westerly at the island. So for this project, we used ERA 5 reanalysis, seasonally averaged 10-meter wind and sea level pressure data, along with several Pan-Arctic ice ocean modeling and assimilation system, or biomass, ice fields which were used to examine the Wrangel Island ice thickness dipole and its causes. So in this talk, I will concentrate on the use of the Era 5 reanalysis 10-meter winds and the biomass thickness and motion fields. So for the analysis, we use seasonally averaged Era 5 wind data to determine the years of strongest easterly and westerly winds at the island. So then we used seasonally averaged biomass data to identify composite ice characteristics associated with those years of strong easterly and strong westerly winds. And then the difference of these composites were taken to identify the dipole and its causes. So this figure shows a time series of detrended Era 5 zonal wind data at Wrangel Island, which is all seasonally averaged. And using the detrended data, we determined the top 25% of the years with the strongest easterly and strongest westerly winds. Those years are denoted with the black and blue circle markers. So the blue shows the easterly, the strongest easterly winds, and the black, the strongest westerly winds. With these dates, we use seasonally averaged ice thickness data to identify those composite ice characteristics associated with the easterly and westerly winds throughout the year. The difference between the composites was then used to identify the dipole. So as calculated, the sign of the anomaly in these fields corresponds to climatological easterly flow at the island, but a reversal in the circulation would result in a flipping of the sign of any anomaly in the following slides. So here is the biomass ice thickness difference, the seasonally average difference between those years of strong easterly and strong westerly winds at the island. And we can identify the ice thickness dipole in the winter here and in the spring, with the thick ice on the eastern side and thinner ice on the west side of the island. This is true under climatological easterly flow, but would be reversed when it's westerly flow. The dipole is strongest in the winter and appears on the order of around 2 meters. In the summer and fall, the dipole looks a bit different, but there's larger decreases in ice thickness on the west side as compared to the east side. The two polygons on either side of the island are used to quantify the strength of the dipole. So for a particular month, an average of the ice thickness difference is taken in each polygon, and the difference is then calculated. So this is shown here. This figure has the mean dipole strength throughout or through the use of those two polygons. So the black line shows the difference between the two. The red is the eastern polygon and the blue is the west polygon. So here we can confirm the dipole is strongest in January with a thickness difference of around 1 meter. The dipole is generally largest in the winter and weakest in the summer, with a spike in June as well. The poles are of near equal and opposite magnitude, although in June, the western pole has the spike, while the eastern pole has very little change. This likely relates to the opening of the seasonal Polynya, which does open in June to the west of the island. So to show a major cause in the formation of this dipole, this figure shows the difference in seasonally averaged ice motion between those years of strong easterly winds and strong westerly winds. And we can see that the circulation is in general agreement with the surface wind circulation of the Beaufort Gyre, which forces this easterly motion to the island. And then we get the blocking of the ice, which ends up creating the dipole. The strong easterly winds at the island are thus associated with this increased anticyclonic ice motion and easterly ice motion at the island, which confirms that the climatological dipole is associated with increased easterly ice motion at Wrangel Island. Again, if the Beaufort Sea High were to collapse, the sign of these anomalies would be flipped and we would get a reversal in the motion. So what we found is that climatological anticyclonic circulation of the Beaufort Gyre around the Beaufort Sea High creates a sea ice thickness dipole at Wrangel Island. During climatological easterly flow, ice is advected from the east and accumulates on the eastern side of the island, while ice continues to be advected away from the western side of the island. Beaufort Sea high collapse and Beaufort gyre reversals result in a dipole with the opposing sign. The dipole is also associated with the opening of a seasonal polynya, which opens typically in June. Future Beaufort Sea high collapses and other Arctic climate changes like thinning ice will have impacts on the formation of this dipole at Wrangel Island, and this can have consequences on the polynya formation, ocean circulation in the region, and local marine life. Thank you. I'll take any questions.
Okay, thank you very much, Spencer, for great presentation. And yeah, you actually give us lots of times for questions and comments. Okay, so if you have any questions or comments, please put into question and answer tag. For those, the speakers in the Zoom, you can ask questions or put into chat. Well, yeah, I have a naive question to ask. So now, yeah, obviously, clearly you have done a very good job, in identifying this ice thickness dipole around Wrangel Island, and also, the reason, underlying it, associated with this strong east, the winds. And so actually when dipoles are formed, what about, do you see actually the more like polar bears present over that region? Do we know actually the ice much thicker and safer, and so do we have any observations?
Yeah, we were hoping that there would be, but there's not really any fine scale observations like that with like the high resolution enough to tell whether polar bears would prefer to be on one side of the island or another. We kind of just know that they are on the island and around the island. But hopefully we can find a way to look at that in the future. That would be really interesting.
Okay, great. Okay. Yeah, thank you very much, Spencer.
Thank you.
Yeah, I think we are kind of 2 minutes in advance. Maybe we'll wait for 1 more minute, and the next speaker, Kevin, Josh, you can start to prepare,
Hi, Guoqi. Just to mention, there are 2 questions in the
Oh,
Q&A.
oh, okay, so
On the
let's
platform.
go and check. And when I was checking, I didn't see that. Okay, question, let's move down. I don't see actually. So, can you read out? Maybe is Spencer still there?
Yeah, we'll post the question in the chat and then also read out the question. The first question is, are there any other islands in the region as well that show similar dipole behavior? That's question number 1. Question number 2 is the dipole anomaly is plus minus 1 meter. What is the mean thickness?
Okay, so for the first question, are there any other islands in the region? Yes. Basically any land where the ice is flowing and it gets trapped against, it accumulates and sort of has the same thing happen. So especially in the East Siberian Sea with the new Siberian islands, there's thicker ice on that eastern side of those islands and then thinner ice on the west side of those islands during the climatological flow. So yes, there are other places. Second question, the dipole anomaly is plus or minus 1 meter. What is the mean thickness again? Oh, I see. The mean thickness in the I'd have to go back and check, but it's somewhere like 3-4 meters. It is changed over time. And it depends on the season, especially, but it doesn't get much thicker than 4 meters or 4.5 meters.
Hey, thank you very much.
Thanks.
Spencer. Yeah. Okay. So next presentation is going to given by Kevin Josh on wind-driven transient Polynyas in Nares Strait.
Yeah. Hello, can you hear me, see my screen okay?
Yes, I can hear you well, and the yes, presentation is up.
Okay.
Good.
Awesome, thank you. Hello everyone, and today I'm going to be talking about these transient wind-driven polynyas that we've discovered within Nares Strait. This is a work done by me, Professor Ken Moore, and another student in our group, Caitlin McNeil. So firstly, what exactly are these polynyas? Polynyas are these open water regions that are situated within a surrounding sea ice covered region. And they generally form in two distinct ways. They can either form when you have warm subsurface water that upwells and melts surface sea ice, or you can have winds that drive away sea ice cover over a region and it reveals the underlying water. And they tend to look something like this, where you have this open water site and then surrounding sea ice enclosing it. And now these structures are extremely important to both local and global climates. Meteorologically, they are able to facilitate these really strong interactions between the water that's now revealed and wind that passes over this water. So you have this transfer of things like moisture and heat that can affect downwind climates that this wind will eventually cross over. Oceanographically, when you have this open water site and this water begins to freeze, it deposits salt into the water, and this can affect the salinity profile of the subsurface waters, and it often allows for these convective cells to form and allows for the mixing of deep waters and surface waters. And on top of this, because you get this mixing, you often get these nutrient-rich deep waters that are able to come to the surface and then be exposed to higher levels of solar insolation, and it allows for really complex ecosystems to form around these sites. So you get the formation of things like phytoplankton blooms, and where you have an abundance of these primary producers, you're of course going to get higher order organisms that are going to come and use this place as a habitat. So there have been sightings of different marine animals, seabirds, beluga whales, walruses, and even polar bears. So a really complex ecosystem can thrive in these polynya sites. Now, Nares Strait is a waterway situated between Ellesmere Island in northern Canada and Greenland, and it looks something like this. You can see the topographical view of the site over here, and it's a major pathway by which sea ice from the Arctic Ocean is exported through the strait and eventually goes into the North Atlantic Ocean. Now, when sea ice accumulation becomes thick enough, especially during these winter months, you can get this blockage of the strait that occurs because these ice arches form. And when these arches form, ice is not able to pass through the strait, and you get the formation of what's known as the North Water Polynya that forms near northern Baffin Bay at this site over here. And this is what the conditions look like, where we have very thick sea ice cover throughout the northern part of the strait, and the southern part is completely open water. And now this is very important because this is the largest Arctic polynya, and it supports a major ecosystem, and it also supports many communities that live in and around this region. Our recent studies, though, have been showing that due to things like global warming and thinning sea ice, this ice arch is not as stable as it has been in the past. And due to that, the formation of the North Water has not been continuing as it has been in the past. Now, this is something I'm going to get back to a bit later on in the talk, but my own work was focusing on this region further north within the strait, known as Kennedy Channel, and specifically looking at two islands in this region called Joe and Franklin Islands, respectively. Now, so previously we have known that the presence of islands within the path of ocean currents or wind currents can affect downwind climates. So that has been well documented in the past. So we wanted to see whether these islands that are present within the path of sea ice flow through the strait are able to shield the downstream regions and prevent ice from covering those regions and essentially create their own little polynyas. And we expected that this effect is correlated with how strong the winds are and how strong of an ice advection effect we get. So if we look at one day here, October 26, 2022, and look at the sea ice distribution over this region, what we can see is that in Kennedy Channel, directly south of these two islands, at the north and central parts of Kennedy Channel, you can see these major reductions in sea ice concentration. And these are the little polynyas that we were looking for, and we wanted to see, does this singular event replicate itself in time and over extended periods of time? In order to do that, we used two specific data sets. We used the AMSR and AMSR2. These are instruments that measure sea ice concentration data to a resolution of approximately 3 kilometers. And they've been collecting data every day for the past 20 years. So we had a nearly 20-year daily data set. And we also used the CARA reanalysis project, which stores things like 10-meter wind speed, 10-meter wind direction, as well as sea level pressure to a resolution of approximately 2.5 kilometers. And this data set extends back nearly 30 years at a 3-hourly rate. So these two data sets had really nice spatial and temporal matches in resolution. So it was a good way to compare these different parameters. So what exactly did we do? We took these sea ice concentration maps for every single day for October that we had. We chose October because it was the best time period to avoid the sea ice arch season where there's no ice flow at all. But we also have a fair amount of sea ice flow through the strait. So we took these maps for every day in October that we have, and we averaged the ice concentration in this polygon to find the average ice concentration within Kennedy Channel. We then constructed these time series to show how this ice concentration changes over a typical month, for example, and we identified the high extreme ice concentration events and the low extreme ice concentration events by finding dates that had concentration values that exceeded the upper 90th quantile value and lower 10th quantile value. So essentially what we were doing was, for October, for every year that we had on record, we used the sea ice concentration data from the AMSR instruments. We used this to identify maximum and minimum sea ice concentration events, so the amount of sea ice and the days that had really high amounts or very low amounts. We connected these dates back into the sea ice concentration data as well as the wind and sea level pressure data, and we were able to construct these composites and these spatial averages to visualize what kind of mean sea ice behavior and wind behavior we have in these different regimes. We also repeated this whole analysis for November, and we found very similar results as to what I'm about to show you in the next couple of slides. And we also flipped our analysis, whereby instead of starting with sea ice concentration data, we chose to start with wind data and identify maximum and minimum wind speed and wind direction events, again connecting it back to sea ice concentration data and wind data and looking at these different regimes. And again, it's very similar results as to what I'm about to show you in these next couple of slides. So after all this, what did we find? These are the three composites for the sea ice concentration, the spatial averages of sea ice concentration in these different conditions I was discussing. And when we look at these minimum sea ice event concentration events, what we see is that this reduction of sea ice is not caused by a general minimization throughout the length of Kennedy Channel, but it's caused by these specific local reductions south of these two islands. And these are the polynyas that we were looking for. In the mean condition, on the left, this is when we averaged every single October day we had on record to look at what the mean sea ice behavior was like. What we see is that you can still see the same island signal south of the islands, although it's not as significant of an ice reduction effect as we see in the minimum case. And in the maximum case, you see high levels of ice concentration throughout the entirety of the strait, with a small signal that's caused for slightly different reasons south of what's known as the Washington Land Peninsula here. And again, I mentioned that we wanted to take the sea ice data and relate it to how do the winds look. So now when we look at the wind composites, for those days that we have very low ice concentrations, we see that in the minimum events, the winds going through Kennedy Channel are strongly enhanced, mostly because of the narrowness of how narrow the strait gets at this site, but the winds reach speeds of up to nearly 15 meters per second flowing southwards. In the mean case, again, we have southward flowing winds, but they're not as powerful as in the minimum case. And again, we see that the polynya production that we get is not as significant. So this kind of suggests to us that it is perhaps indeed the wind strength that affects how significant of a polynya production you get south of these two islands. And in the maximum event case, we can see that the winds through the channel are very weak, and in some cases they're flowing actually northward, which is quite uncommon for Nares Strait, but especially up toward the Lincoln Sea, the flow is much more strong northward as it is southward. And just for a more quantitative view of this is a plot of those same three regimes, but we're looking at ice concentration by latitude. And what we can see is that in the minimum event compass of this blue line, directly south of the latitudes of these two islands, you get this major reduction in sea ice concentration, which again is signaling to us that it is indeed these islands that are potentially causing this reduction and causing this effect to occur in the strait. So overall, what did we derive from this work? We essentially discovered two previously unknown polynyas that were found within Nares Strait. So while previously we had this Northwater polynea, which was quite well, there's a lot of studies going on about it, we found these two new polynyas that are further northward in the strait. And the really important thing that we found here was that these polynyas exist in conditions when the sea ice is flowing and is in motion through the strait. So the Northwater polynea, as I mentioned, relies on the formation of this ice arch, and it relies on static ice conditions in order for it to form and in order for the resulting Northwater polynea to form. Now, in a future where, like, unfortunately, the globe continues to warm and sea ice gets thinner and thinner, the formation of this ice arch might not be as stable as it has been, and it might not form as nicely as it has been in the past. And as a result, the Northwater will likely look different than it does today. So in those future conditions, when sea ice is in motion more often, these polynyas that we found within Nares Strait are still going to be present. So it kind of acts as an alternative option for these organisms and these marine animals that rely on the Northwater. They could turn to other nearby polynyas like the ones we found further north in Nares Strait and use it as a habitat in a future where the sea ice environment looks very different than it does today. So this kind of research is really important, and it kind of stands to do a bit more work to look at if these polynyas are actually currently used at all by any kinds of marine animals. But that's all I want to talk about today. So thank you all for listening, and I'm happy to take any questions that anyone has.
Okay, thank you very much. Now it's the time for questions and comments. Please put your question and comments into question and answer tag.
Hi, Kevin. Can you hear me?
Yes.
Yeah,
Yep.
I posted a question in the chat. I had a similar question to Kent Moore's talk previously, and then the question is, would the wind have a cumulative effects in the previous months? In your talk, I think you were focused on October. How about the wind in the previous months? And in Ken's talk that was focused on May, how about the effects of the wind in this region that's been during a relatively longer period? Thanks.
Yeah, I think for what I was looking specifically at distinct events that occurred. So if you looked at the time series that I had earlier, what you see is that the ice concentration changes and it increases. So it's quite variable in this region. So we were trying to identify specific events where the wind was very strong and you get this dip in ice concentration. And then in the next few days, it might have increased again. So I think what we were looking at was not really a cumulative effect. It was like distinct events that we were looking at globally or holistically to see how they look in many different cases. So I think it's not really a strong cumulative effect for what I was looking at. And it was more like, do you get these distinct events occurring and how often do they occur?
If I could just jump in, Dan, I think you're I think your question is if the ice is mobile and the winds are strong, then you'll see these effects in any month. I think maybe that's the question you're trying to ask. The challenge, of course, is that in the summer there's no ice presence, so you don't get these effects. And then as soon as the arch forms, let's say in December, then the ice is no longer mobile. But if the ice is mobile, you'll see these sorts of effects. At least, so it's not cumulative. It's just that if there's mobile ice and the winds in these regions are enhanced, then you'll get open water.
Thanks, Ken.
Okay. Thank you.
Thank you.
So next presentation is given by Claire Parrott, and the topic is Tidewater Glacier influence on the marine environment in the Canadian Arctic archipelago.
Great, thank you. Yeah, hi everyone. My name is Claire Parrott, and I'm a master's student at UBC working with Stephanie Waterman, as well as Paul Myers at the U of A. And I'll be talking to you today about some of my work on Tidewater Glacier influence on the marine environment in the Canadian Arctic archipelago. So, first of all, what is a tidewater glacier? A tidewater glacier is defined as a glacier that touches the ocean. And tidewater glaciers are important and unique features to the Arctic coastal ocean as they terminate in the ocean and they produce subglacial discharge that can discharge at depth in the ocean, enhancing mixing nearby the glacier face. This allows for nutrient delivery through two different mechanisms, that being the entrainment of nutrient-rich deeper seawater, as well as meltwater, which can be enhanced in both macro and micronutrients. So this nutrient delivery to the surface stimulates biological productivity nearby these tidewater glaciers. And these glaciers are known to be biological hotspots in the coastal ocean across the Arctic. Further, the addition of freshwater drives estuarine circulation in the coastal ocean, as well as can alter the vertical water column structure through the enhanced mixing near the terminus, the glacier terminus. This is relevant across the Canadian Arctic as it's a region rich in glacier mass. It has the third largest amount of glacial mass in the world, next to Greenland and Antarctica, and the CAA is further an important region for Arctic export, as 2/3 of the Arctic export flows through the shallow region of the CAA. Despite this region being rich in tidewater glacier influence, as well as being oceanographically significant, most of the research on tidewater glacier ocean interactions have taken place across Greenland and Svalbard, and that gives us no information on how these unique sources of fresh water might be altering or affecting the oceanography of this region. So to understand more how tidewater glaciers are impacting the Canadian Arctic archipelago, which differ from these other regions as glacier geometry and oceanography is different in the CAA in comparison to the other regions where it's studied more heavily, we use Jones Sound as a natural laboratory to study tidewater glacier ocean interactions in the CAA. This is a great place to perform this study as it's the third largest export pathway on the CAA and is a tidewater glacier rich region having 4 major tidewater glacier ocean systems highlighted in the orange boxes here. So it's a region abundant in glacial meltwater and is important in the context of our CAA export. Further, this region is home to the community of Ayuitak or Grisfjord, who use the coastal ocean for traditional hunting, culture, economics, and livelihood. So this brings me to my research questions. In understanding the influence of these tidewater glaciers on the marine environment in the CAA, I look for the dominant modes of variability in these tidewater glacier ocean systems to understand what is driving the variability across the coastal ocean. And I also look for a systemic influence from tidewater glaciers on the water column structure. To do this, I use an observational data set composed of 4 years of summertime CTD and bottle samples across specific sites within Jones Sound. So these sites I classify based on their freshwater source as well as their coastal geometry. So the freshwater source can either be a tidewater glacier present across the 4 major systems I outlined previously, or a riverine source on the coast. Further, I classify these sites based on their coastal geometry, that being whether or not the coastline is open or fjorded. So I take these sites and I derive freshwater metrics for these sites and look for that allow us to think about stratification and freshwater storage across the region. So that being convective energy, which is an integrated metric of stratification. You can think about it as the amount of energy required to overturn the water column down to some integrating depth, as well as the freshwater thickness, which is a one-dimensional metric for freshwater storage. Further, all of these observations that I use in this, or most of the observations used in this data set, are collected in collaboration with the community of Asawitak, who we partner with in our Ice to Ocean project. To look for the dominant modes of variability, I perform a PCA analysis on a subset of variables, in this instance for the freshwater and stratification environment, or freshwater and stratification metrics within this data set. So when we're looking at the surface samples across the region, we have 2 dominant modes of variability, PC1 and PC2, that explain about 60% of the variability across the samples. PC1 describes a fresh and stratified environment for positive samples, and PC2 describes a warmer environment for PC2 positive observations. If you've never seen a PCA before, data points that cluster closer together are more similar, and data points that are clustering further apart are more different. So within this definition, when we are comparing our different freshwater sources, we see that our riverine sites stand out as being warmer than glaciarized sites at the surface. When we look within our glaciarized classification, we can see that coastal geometry matters, and our fjorded and glaciarized sites are different, and PC1 positive being more fresh and stratified in comparison to our glaciarized and open sites. If we look deeper in the water column, we have a slight modification to the modes of variability, that being PC1 is colder, describes a cold and salty environment in the positive direction, and PC2 describes a stratified and turbid, environment in the PC2 positive direction. We don't see any separation in the deeper water column based on freshwater source, but what we do see is, again, the partitioning of our sites based on coastal geometry, where, again, our fjorded sites are higher in convective energy and freshwater thickness in the upper 100 meters of the water column. I perform the same PCA analysis, including a larger suite of variables that describe the biogeochemical environment. When we look at our 2 modes of variability in the surface, our PC1 is positive, describing a cold, salty, nutrient-enhanced water sample, and PC2 positive, describing a stratified and cold environment. When we look at how our data points are distributed in PC1, PC2 space, only our glaciarized sites are PC1 positive, indicating that we see nutrient enhancement only at the glaciarized sites across the 4 years of data. Further, we see that our riverine sites are not nutrient enhanced and vary predominantly on PC2, ranging in stratification and temperature. When we look to our whole water column and we look in the deeper subset of samples, you can see that there's our modes of variability are similar to before, where we see salty and nutrient enhanced on PC1 being positive, and stratified and non-turbid environments being PC2 positive. What we also see here is that all of our different site classifications are nutrient enhanced deeper in the water column, further exemplifying that there's always nutrient enhancement below 30 meters, but only the glaciarized sites are seeing the delivery to the surface where we have light available for productivity.
2 minutes.
In thinking about the systemic influence, on the water column here, I take anomaly profiles by calculating the mean coastal profile for each of the different site classifications and subtracting that from a representative open profile so we can look at how the coastal ocean is being modified in comparison to the open. In freshwater thickness, we see that there's always higher freshwater at the fjorded sites throughout the whole water column to varying degrees throughout each year. When we look at stratification, we can see that, again, our fjorded sites are more stratified, notably more stratified at depth, where we have some overlap in some years between the different site classifications, but consistently a positive anomaly stratification at the fjorded sites at depth. Finally, when we look to turbidity, we can see that tidewater glaciers are always have a nutrient or have a turbidity enhanced upper 40 meters of the water column. And thus there's sediment delivery from these tidewater glaciers to the surface. And quickly to conclude, when we look at the dominant modes of variability, our tidewater glaciers are important for nutrient enhancement at the surface. A byproduct of this study is showing us that coastal geometry is important for freshwater storage and stratification in this the coastal ocean across this region as well. And when we look for systemic influence of the tidewater glaciers on water column structure, we see that the tidewater glaciers are important for delivering sediments, creating turbid environments in the proximate ocean, which can affect light availability at the surface. And again, that we see the fjorded sites storing more fresh water and more with higher stratification in the upper 100 meters of the water column. Thank you.
Thank you very much, Claire. Nice presentation. So now we have time to ask questions. Please put your questions or comments into the question and answer tag. Yeah, there's one question now, Claire.
Yeah,
so did you see? Oh,
yeah, I
okay.
have the chat open here. Yeah, so I sort of use different subsets of the variables.
Oh, can you first maybe I speak out the question. So, Claire, nice talk. Can you elaborate the properties in your PCA axis? For example, what is SA, PT, and other variables?
Yeah, yeah. So for the physical environment, or looking at freshwater and stratification, PT and SA are potential temperature and salinity, as well as freshwater thickness and convective energy. So these are metrics that describe the few different aspects of stratification and freshwater storage. And then when I turn to the biogeochemical environment, I take those same physical metrics, and then I add a few different biogeochemical variables to the PCA. So adding dissolved oxygen, major macronutrients, so silicate, nitrate, and phosphate, as well as chlorophyll, fluorescence.
Great. Yes, thanks again, Claire. And now we move to next presentation, given by Sarwesh Mali, and the presentation is on tide-induced extreme bottom current resuspension in Halifax Harbour.
Super. Can you see my screen and hear me?
Yes, I can hear you and see your presentation. Good.
Super. So first of all, thank the audience members for sticking around for the last presentation in today's session. I'm Sarwesh, a PhD candidate at Royal Military College of Canada, working under Professors Shan and Shore. I'd also like to acknowledge the support from Dr. Crawford from DRDC Atlantic. The title of my talk today is going to be Tidal-induced extreme bottom current resuspension in the Halifax Harbour. And over here in your left-hand side, I've shown the picture of the Halifax Harbour with its various sections indicating water depth. So first of all, I'd like to introduce the importance of bottom sediment resuspension and then provide a brief background on Halifax Harbour. And then I'll speak about the objectives and methodology used in this study, and then highlight some of the main results from our study. So bottom sediment resuspension has been extensively studied in the literature for various reasons, such as it could be important for nutrient recycling, as nutrients trapped in the sediments can be released, affecting the benthic environment, as well as pollutants trapped in the sediments can be remobilized, affecting affecting marine life as well as water quality, as well as sediment transport, which can modify the seafloor. So our study has been influenced by sediment transport, in particular Halifax Harbour, due to its strategic location as well as a unique environment. So for those that do not know, I'll provide a brief background on Halifax Harbour. Here I am showing a map of the Halifax Harbour, which is located in the east coast, Nova Scotia. It is part of the Scotian Shelf. It is the second largest east coast port of Canada, and it really forms a gateway connecting the port of Halifax to the Atlantic Ocean, as well as its home to the Royal Canadian Navy's Atlantic Fleet. As can be seen in the map, the deepest part of the harbor is the Bedford Basin, which is the fjord-type estuary. Its depth is approximately 71 meters. The Narrows is the narrow and shallow part of the harbor, with depths approximately 20 meters. And the rest of the harbor is shallow, containing Northwest Arm, Eastern Passage, as well as the Outer Harbor, which connects the enclosed harbor to the open sea. Here, I'm showing the colorful map of Halifax Harbour, where different colors represent different type of sediments that can be found in the harbor bed. This has been readapted from a Geological Survey Canada report by Fader and Miller. We've used a standard Wentworth grain size classification scheme to further reclassify the type of sediment to an average grain size, as you can see on your right table. For example, the clay sandy silt type of sediment has an average grain size of 4 microns. So bottom currents exert shear stress on the sediment bed, and when this shear stress exceeds a certain threshold, sediments are lifted up and they become resuspended. So the Shields parameter, which is shown right over here, provides us conditions when this happens. So for the Shields parameter, the shear stress is obtained from the simulations, and the grain size is obtained from the sediment map. On the right side, I'm showing the critical Shields criteria, which is the threshold value calculated. For our sediments, we've assumed that they are non-cohesive and wave-induced effects are ignored to simplify the modeling. Sediments are resuspended when the Shields parameter exceeds the critical Shields criteria. So now what I'd like to do today is to show how simulations of tidal-driven bottom currents can be used to really identify resuspension zones in Halifax Harbour. I'll answer questions such that how does tides affect the depth average currents, as well as peak current dynamics in the harbor, as well as what are those regions in the harbor where they are prone to sediment resuspension. So before I go into the results, I'll speak a little bit about the methods used. The simulations were performed using a finite volume community ocean model, or FVCOM, using triangular unstructured meshes with elements and nodes with 20 sigma or depth layers. Tides were used as input boundary conditions, and the simulations were barotropic. So in order to assess the accuracy of the simulations, we've compared the sea surface elevation at a tide gauge located at a BIO station, as it can be seen in the map of the harbor. On the right side graph, it shows the comparison of the water level between observation in black, which includes the tidal as well as non-tidal components, versus simulation in dash red, which only includes the tidal components over a duration of 2 days from 30th September to 2nd October 2019, which is during a spring tide. The tidal range, as can be seen from the graph, is 2 meters. The FVCOM is able to reasonably predict the water level. However, we can see that there's differences between the observation and simulation, especially at high and low tide conditions. And these variations could be caused due to the omission of the non-tidal components in the simulation. So here I'm showing the depth average currents in the harbor over a tidal cycle. The black arrows represent the velocity vectors for the depth average currents. Also, a reference 10 centimeter per second velocity vector is shown for reference, as well as these red dots here indicate the time relative to the tidal cycle corresponding to low tide, flood, high, and ebb tide conditions. The color bar at the bottom represents water depth, and the red arrows indicate the general movement of water in the harbor. The harbor's water circulation involves landward flows, where water flows towards the Bedford Basin, and seaward flows when water flows away from the basin towards the outer harbor. As you can see from the depth average currents, the currents are weak in the Bedford Basin area. However, they are in counterclockwise direction because of local bathymetry as well as coastline. Stronger currents are observed at the Narrows, as well as recirculation zones near McNabb's Island, also shaped by the local coastline. And as expected, during flood tide, we have landward flows towards the basin, and during ebb tides, we have seaward flows towards the outer harbor. So in order to visualize the peak bottom currents in the harbor, I'm now showing the maximum current velocity obtained just above the seabed in the harbor, and maximum bottom currents are observed to be 26 centimeters per second, observed near the entrance to the Bedford Basin. The maximum bottom currents vary throughout the harbor, as can be seen in the map, where weak maximum bottom currents are obtained in the deepest part of the harbor, which is the Bedford Basin. Strong bottom currents are observed near constricted passageways, reaching up to 18 centimeters per second near the Narrows. So what we've done is we also compared the timing of the maximum bottom currents, as shown on the figure on the left side, where blue, green, and yellow dots indicate time relative to the tidal cycle. And what we observed is that mostly in the Bedford Basin, maximum bottom currents peak during seaward flows. However, there are local exceptions that also peak during landward flows as well. Bottom currents in the Narrows, as well as near McNabb's Island, peak during landward flows. And the behavior of bottom currents near Northwest Arm, as well as the Eastern Passageway, are a little bit more complex, as they peak both during landward as well as seaward flows. So here I'm showing the map of Shields parameter for the entire harbor for a sediment type of grain size 4 microns, or the finest sediment type. We can see that the red contours indicate the contour for the critical Shields criteria, which means regions inside this red contour indicate regions that are prone to resuspension. And when we observe the map, we can see that these regions are located in the inner harbor, as well as near McNabb's Island, near Northwest Arm. Additionally, there's a small area present near the entrance to the Bedford Basin. Large areas in the harbor show no sediment resuspension, and they could be due to coarser grain sizes or low bottom currents. Also near the narrows, we have stronger bottom currents, which prevent deposition of fine grained sediments, as well as in regions where there is weak bottom currents, they correspond to deposition zones, highlighting the need for targeted monitoring practices in the harbor. So with that, I'd like to summarize the main findings of our study. Average circulation in the harbor can be visualized using depth average currents that depend on tides. The timing and location of the peak bottom currents show how tidal forces affect the sediment transport mechanism. By leveraging Shields parameter, as well as identifying critical Shields criteria, we're able to determine resuspension zones. And those zones are regions south of the Narrows, west of the McNabbs Island, towards the Narrows, and near the entrance to the Bedford Basin. And some of the work that I'm currently doing right now is investigating actually the effect of storms and hurricanes on sediment resuspension in the harbor. And with that, I'd like to stop. And now I'm happy to answer any questions from the audience members. Thank you.
Hey, thank you very much for the nice presentation. And we can have questions for Sarwesh. And please put your question into question and answers tag. Have a look. Yes. So Sarwesh, yeah, we have one question here. What is the approximate size of horizontal grid elements in the Narrows? I'm curious because horizontal current shear is known to occur at least some of the time.
Right. Thank you for the question. The approximate grid size at the Narrows is around 90 meters, and the grid size at the outer harbor is around approximately 900 meters.
Another question. How different would the results for bottom currents from a bioclinic rather than biotropic model?
Sorry, Guoqi, could you repeat the question again? I didn't catch you.
Yes. How different would the results for bottom currents from a bioclinic versus a biotropic model? So
Right.
your model now is a tidal model, but if you're including density effects, what do the results look like?
Right. So that's a great question, and that would be the next logical step would be to include density-driven effects, because we know that it is a estuary, which means there is density differences. So what we've done is like first of all simulated a simple sort of model without density effects, and then compare that to a model which we can include density effects and see what those differences would be. So that would be the next step. Yes.
Okay, thanks again, Sarwesh. Yeah, we do look forward to your results, and hopefully we'll have you come back to present next year. All right.
Thank you.
Okay. Okay. Yeah. So with that, I think we will conclude our third part of the session, and I would like to thank all the speakers, for your interesting talks, and for all the audience for your active participation. And yeah, at this moment, on behalf of Jing Yushin and Shiliang Shan and myself, so yeah, thank everybody. And especially now thank Wendy for help, so we can run this 3 sessions smoothly. And yeah, Shiliang, do you have anything to say?
Just want to thank all the speakers for today. We have all 3 sessions, and then and also interesting talks and the great discussions online. I hope everyone enjoy the rest of the Congress and hope see you in other talks and then around online.
Great. Okay. Thank you. Okay. Bye-bye now.